Alright, I'm going to explain how to use Gauss elimination to solve a system of linear equations. We have a simple system of three equations here. First, we want to mention that your system must be written in a standard way. So we see x and y and z over here, x and y and z, and these variables are in the same order on the left-hand side, and this non-homogeneous part is on the right-hand side, 4 and 5 and 6. X and y and z are the unknowns. The first thing we need to do is to extract these numbers. They are the coefficients of these equations. We form a matrix called an augmented matrix. This matrix represents the original system. After we've done that, we want to use three kinds of elementary row operations to reduce this augmented matrix to a simpler form so that we can solve the system easily. And if we look at these three types of elementary row operations, we see we have rescaling. It means to multiply a non-zero number to any row. Or swapping. That means to interchange any two rows. And third one, adding a multiple of a row. It means to add a multiple of a row to another row. In order to get rid of this 1 and 2 and 6, or just make these entries 0, we see that we can use the following operation. If we simply multiply -1 to this row and add this row to this one, that means we are using the third type of row operation. Then we can make this entry 0. So we write down the operation like this. It's -1 times R1 and then plus R2, row 2. Okay. And this gives us the following. So this is 1 and 2 and 2 and 4. The first row remains the same. We're not doing anything to it. And then the second row, multiply -1 to the first row, add to this row means simply subtract the first row from the second one. So 1 minus 1 is 0. So we are quite successful. And then 3 minus 2 is going to be 1. And then 3 minus 2 is 1. And 5 minus 4 is 1. So we are subtracting these entries from the corresponding ones in this row 2. And we are not doing anything to the last row, so it's still 2 and 6 and 5 and 6. Okay. Now we are done with the first entry over here. We finish this process column by column. And this number over here, the first one we used, this number is called the pivot. And we use this entry to eliminate other non-zero entries in the same column. So now we are trying to eliminate this 2 over here, make this 2 to 0 by performing one of these row operations. We use the same idea. If we multiply -2 throughout this row, and then we add this one over here, then we have 0. So we have over here, we have 1, 2, 2, 4 is the same thing. And then we have 0, 1, 1, 1. This row is not changed, but now we have -2 plus 2, this one is 0. -2 times 2 is -4 plus 6 is going to be 2. And then -2 times 2 is -4 plus 5 is 1. -2 times 4 is -8 plus 6. This is -2 over here. So this one means it's -2 times R1 and plus R3. This is again adding a multiple of a row. We add -2 times the first row to the last row. Now the first column is done. We have this pivot over here is 1, and then the rest of the entries are 0. Now we look at the second one. We won't do anything about this 2 above this one, but we look at the rest of the rows over here, starting with these 2 zeros. So now we will try to get rid of this 2, make this entry to be 0. To do that, we use this entry over here as a pivot, and then we add a multiple of row 2 to the last row. So we have 1 and 2 and 2 and 4. And then we have 0 and 1 and 1 and 1. And then we have 0 over here. Now, negative 2 times 1 plus 2, this is 0. So we are doing negative 2 multiplied by second row and added to the last one. Okay, so this is what we are doing. And this is negative 2 times 1 is negative 2 plus 1 is negative 1. Negative 2 times 1 plus negative 2, this is negative 4. Okay. Now, the system represented by this matrix over here is already very easy to be solved. But we want to go a little bit further to see how we can actually use the first row operation, first type of row operation, risk scaling. Because we see the last one, we have negative 1, negative 4, we are going to multiply negative 1 through. So this is called risk scaling. So we have negative 1 times R3. And this gives us 1 and 2 and 2 and 4. And 0 and 1 and 1 and 1, and then 0 and 0 and 1 and 4. Okay. Now we are done. We see that if we look at this part, we have an upper triangular matrix. Over here, we have non-zero entries, and over here we have all zeros. Now this augmented matrix, if we go back to the linear system, we have the corresponding system like this. We have the first one is not even changed, x plus 2y and plus 2z is equal to 4. And second one becomes much simpler, y plus z is equal to 5. No, it's equal to 1. Okay. And then here, the last one is z is equal to 4. Okay. Now, because we only used 3 kinds of elementary row operations, this new system has exactly the same solution set as the older one. So now we can solve this system easily because we can now use so-called backward substitution method to solve for all the variables. So let me write down. So this step is called backward substitution. Backward substitution. So we solve the last one first. So we see z is equal to 4. Because z is equal to 4, so y plus 4 is equal to 1, then y is equal to negative 3. The first equation is longer, so we use one more step. So this is going to be negative 3y, plug it in, and then 2 times 4, and then this is equal to 4. It means we have x minus 6 plus 8 is equal to 4. Okay. And from here, we have x is equal to 2. Okay. In vector form, we can write down something like this. X, y, and z, this vector, solution vector, is equal to x is 2, y is negative 3, and 4. So for this linear system, we have exactly one solution.